Welcome to Unit 1, Powers and Roots. We're talking about the real number system. So, as we've discussed with our symbols, we are now going to talk about it here. We have natural numbers. This is our smallest group of numbers. They are the counting numbers. So, as you've all written down, we're going to write counting numbers beside it. Okay? Counting numbers, and they go all the way to positive infinity. Whole numbers, well, they are the set of natural numbers, and they include 0. They only add one extra number in there. So these are natural numbers including 0. So now they add one more number on the number line. So far on the number line, if this is 0 on our number line, natural numbers, at number 1, natural numbers start here. Okay? The minute we go to whole numbers back us up on the number line. We end up going left one number. Well, integers, they're going to back us up on the number line even more. That means we're now allowed even more numbers. We're allowed the negative infinity numbers all the way to positive infinity. That's what those 3 dots mean. They actually have a saying they mean. It means and so on. So and so on means that it will run on and create forever. Okay? That's what that means. Then we've got rational numbers. Rational numbers, now we get into our decimals, again, the repeating ones, or the ones that are terminating, the ones that end, like 7.3, 8.927, they end. Then we also have our fractions here. Okay? So decimals and fractions. But it also includes integers. This includes all these other smaller numbers. Okay? So what I'm going to show you right now as a demonstration just is the diagram of the objects. So the hat is the irrational numbers. It does not have anything to do with these rectangle boxes. However, we have our teeny tiniest box. Our teeny tiniest box is natural numbers. Those are the counting numbers. There's not very many of them. I add one more number. I add 0. Now the natural numbers are inside that set of numbers. They're part of it. Okay, so they're part of that set of numbers, and they included 0. Then we've got the integers. We're even bigger on the number line. We go further left. We've got the negative numbers now. So we take 0 and all the positive numbers, put it inside the integers. Now we include the negatives. Then we've got our giant set, which is rationals. We take all of the integers, the negative numbers and positive numbers on the number line, and then we include fractions and decimals. Okay, and that's how that works. So these are called manipulatives. You're allowed to use them on an exam. So if you forget what they all represent, you're allowed to take them out and look at them. That's totally fine. Okay, so that's our real number system. Let's talk a little bit more about which numbers could fit inside them. So let's take a look at questions. So here's the diagram of what I just showed you in boxes. So as we know, those natural numbers, that was our tiniest box. Then we have the bigger boxes, okay? And then we have this guy right here, we have the hat. Okay, that's our hat. He has nothing to do with those boxes on the left. Okay? All right. Now we're going to take a look at some true and false questions. So, I'm going to use these diagram manipulatives, and we're going to go through every single question together. We're going to circle true and false. So, the box I'm talking about right now are whole numbers and integers. Look at the way it's worded. First one says that every whole number is an integer because it can fit in that box. True or false? True. Did the whole numbers fit inside the other box? Yes, they did, so it's true. Now, let's word it backwards. Is every integer a whole number? No, there's too many numbers in here. They include the negatives. So if they reverse the way they said that, it would be false. Okay, so you have to watch the way they're saying it. The next one. So they're saying on the next one that every integer, negative and positive, is natural. Is that true? No, that's false. There's not enough numbers in our natural. to include the negatives. The next one, every integer is a whole number. So every integer can fit in the whole number section. No, because whole numbers don't have negatives, and the integers do. So again, you are right, it is false. Let's take a look at letter D. Irrationals. All right, now we're talking about the hat. So on the hat, we have non-repeating, true, and non-ending, non-terminating decimals. Is that true? Yeah, we have the run-on decimals. Absolutely, that's true. Okay, we have the decimals that run on and they don't repeat a pattern. Okay, so that one is true. Now, the next one says, okay, irrational numbers, the hat, is still part of the real number system. Is that true? Yes, it's still part of it. It's just on the other side of the other guys. Okay? So remember, there's two branches. The irrational branch and the rational branch. All right, now let's take a look at the next one, letter F. Every rational can be written as a fraction. What do you think? What's the symbol for rational? Q. That stands for a quotient, which means if it's a rational, it should be able to be put into fraction form. So that one is true. If it's a rational, you can write it as a fraction, you bet. Letter G. Every integer. So now we're talking about the integers and the fractions. The integers are in the smaller box. So this one's saying that every integer can be written as a fraction. Therefore, every integer here is a rational number. Yeah, because you can write all of these numbers in fractions. Okay? All right. H. Every rational number is a whole number. Oops, wrong box. It's a whole number. Will it still fit in there? No, it's not fitting in that small box. Yes. Right, there's no fractions in that section, but this is what it means by that. I could write -7 as -7/1, or I could have -7 be the answer of a fraction. So if I've got, let's say, -21/3, this is written as a fraction, but I can solve the fraction, and you have to solve the answer always. So this would be -7. So the way it is written right now, it's written as a fraction, but when it simplifies, it's going to simplify to an integer. So that means it's actually an integer, not a rational. Well, an integer is a rational. But that's why it's not only just rational. It is an integer. Because you always have to solve them. Same as perfect squares. Perfect squares are in the rational box. But even though they're in the rational box, if I've got a perfect square, the square root of 25, I'm going to solve it. That's 5. You always have to simplify if you can. Okay? Good question. All right, let's take a look at a few more examples. So, every natural is a whole. So let's look at our boxes again. Can the smallest set be put into another bigger set? True, yes it can. So every natural is a whole for letter I. Okay, letter J. Letter J says there are more rational numbers. There's more of these guys than there are of these guys. What do you think? Who's got more? What do you think? Who's got more? I want you to give me a reason for it. What is your reason if you say true?
Because it's from negative infinity to positive infinity.
Okay, negative infinity to positive infinity. What's another reason? You didn't have a reason? What's your question? Okay. Somebody else have another reason? No? There are more rational than irrational. Think of how many irrational numbers there could be. It includes all the non-perfect squares. So if we just talked about the numbers 1 to 10, how many of those could be non-perfect squares? Well, think about it. Well, non-perfect squares, there's quite a few of them. But those are the only numbers that are irrational, right? Other than pi and Euler's number. So if we're looking at non-perfect squares only, or just a decimal that's written down that's a run-on number, then there's going to be far more rational numbers. So it is meant to show that this is bigger than the hat. So the rational box should be bigger than the hat. So there's more rationals than there are irrationals. Or, sorry, I just vice versa that. More of these than these. So the hat has more, I apologize. The hat has more. Now, the reason the hat has more is because of this. Watch. It's because, I'm going to show you, I'm going to take the numbers 1 through 10. So, we're on this one. So numbers 1 through 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if I were to put a square root sign over them, okay, which ones are perfect squares? How many perfect squares do I have in those numbers? 2. 4 and 9. So you only have 2 perfect squares from 1 to 9. So, or sorry, 1 to 10. So from 1 to 10, you've only got 2 perfect squares. That means there's going to be 8 numbers that are non-perfect squares. So there's more non-perfect squares than there are perfect squares. Does that make sense? That's why. So that's why this is false, because there's more of those. There's more of the irrationals. Okay? Better? All right, let's take a look at the next question. All right, there's an infinite number of real numbers in between any 2 different real numbers. So what that's saying is, on the number line, draw a number line here. So what it means is, let's say between the number 1 and the number 2, they're saying that in between these 2 numbers, that there's an infinite number of real numbers. So there's an infinite amount of decimals and fractions that can be found in between there. Is that true? It is true. Yeah, it really is.
Decimals.
Because you can make questions into that. I could have 1.1, 1.2, all the way to 1.9. I could have 1.10, 1.11, 1.12. Then you could go to 1.100, 1.111. You could just keep adding decimal points to it. There's that many numbers. There is an infinite amount of numbers in between them, because we can break them down into decimals and fractions. Okay? That's why. Okay, the next one. A rational number plus an irrational is always irrational. So, in order to answer the question, you actually have to take a number. So what they're saying, a rational number, so let's take the number 5, plus an irrational number, let's take pi, is always equal to an irrational number. Is it always equal to an irrational number? Yeah. Because pi runs on forever. So here, this is just going to be 5 pi. I can't take 5 and add it to pi. Well, I could. That's going to give me 5 plus 3 is 8. 8 point whatever, run on forever. Okay? But it's going to give me a run-on decimal because it's adding to pi. So and remember, pi is not the only run-on decimal. Any non-perfect square root will do the same thing happen. So 5 plus a non-perfect square root, same answer. It's going to be an irrational number. Okay? So that one is true. The last question says, an irrational times an irrational gives you an irrational. False. An irrational times an irrational gives you an irrational. Ironic. Now, you'll learn this in grade 10, but it's from this. It's because if I were to take the square root of 5 and I times it by the square root of 5, my answer will be 5. Now, the reason is because this. When I multiply the numbers underneath. What's 5 times 5?
25.
25. Well, it's under the root sign. What is the square root of 25? 5. So anytime you take irrational times an irrational, you will always get a rational number, always. Not when you add them, not when you add them, but when you multiply them. Okay? All right. Let's look at the next page. Our next page. All right, I'm going to give you guys a couple minutes to do this. I'm going to give you an example, and then I want you guys to go through the next couple questions. So, number 2, this is an example of what I want you to do. So, I'm going to use a different example. I'm going to use the example of, let's go with negative 15 divided by 3. That's going to be my example. Now, on that one, remember, you have to practice in the calculator and see if it solves to an integer of some sort. And it does. It solves to negative 5. So because that guy solves to negative 5, I have now gone into which box? I'm now in the integer box. So if you're in the integer box, you're in all the other bigger boxes. So this guy is an integer and a rational, and everybody is a real number. So every single one of these is going to have a real number. Because they're in that real number system. So they're all going to have an R. But we have to decide what other boxes would they fit in. Okay? So this guy, he solved as a negative 5. So that means he was a negative number, he's an integer, and then he fit in the rational box, and he's also a real number because they all are. Okay? So I want you to do these 8, 6, 7, 8 questions here, okay? I'll give you about 5, 6 minutes, and then we'll go through them together, okay? Push pause now and play when you're ready. Okay, so we're going to take a look at the first one. So, when we look at the boxes that they can fit in, number 5 can fit in my tiniest box. If it can fit in the tiniest box, it can fit in every other bigger box. So, that means it is a natural, whole, integer, rational, and we all know they're real. So a beautiful numeric response question, we've seen these on the PAT before. What they like to say is, how many number systems does that number fit in? Well, we would count them now. We would say 1, 2, 3, 4, 5. This guy fit in 5 number systems. Okay, that's what we would do. The next one, negative 5. Well, we're not counting numbers anymore. There's no negatives there. The 0 count, or the 0 one here, that doesn't include negatives. The integers include negatives. So it's got to be integer and rational, because they can fit together. So, integer and rational and still real. Okay? Fractions. Fractions are all in that big orange box, which is rational and real. Square root 10, did you try it? What kind of answer does it give us?
3.8 something.
3.3
Type of answer. I don't want to know the answer, I want to know time.
guessing.
Oh, that's like
Irrational, it's a run-on decimal. So this guy is a run-on, so if he's a run-on decimal, he is irrational with the line on top. But we all know that irrational numbers are still real numbers. Okay? Now, square root of negative 2. If you figured this one out, your calculator would have said error, or syntax error, or math error. The reason it's saying an error is because you can never have a negative sign under a square root. Never, ever, ever. So that means it doesn't belong to any of the systems. Okay? So this one, I put the R there as a distractor, but this guy belongs in none of them. Because it is, let me check on it first so you can get to that. So yes, by process of elimination, you didn't get there, you got it right. It belongs in none of them though, because of the negative sign under the square root. That's why. Okay, it's because it's an error. Whenever your calculator gives you an error, it's none of the real number system. Okay? All right, pi. Who does pi fit into besides my belly? Irrational. Good job. The rest is in my belly. All right, right here. What do you notice with that line? What does the line mean?
It means it repeats.
No, not run on. If there's a line on top, it means it repeats. So this guy's going to be 0.1238, 1238, 1238 forever. So because this guy runs on forever with the same pattern, This guy is rational. Okay, so rational and real. So Q and R.
Wouldn't it be also a whole because that's
No, because remember,
0 and on though.
yeah, but it's decimal. Okay, decimal numbers don't happen until we get to the rationals. Okay, because these three boxes, there's no decimals and no fractions in here.
Oh yeah.
Okay, decimals and fractions are here. All right, good job, you guys. So we're going to take this out. Now, the way we're going to do it is we're going to pick one number, and we're going to find out all of the categories that goes with it. So let's get the symbols. So natural, whole, integer, rational, irrational, and real. Okay? Now, the -4. Which bucket or box would the -4 fit in first? Person?
Integers.
Integer, good. Now remember, this is the size of the box. These guys are the hat, okay? So if it's in all the bigger boxes, any of these, it would be in the bigger ones below it, except for the hat. So he's an integer. If he's an integer, he has to be rational, and they're all real. So the -4 is going to go on the integer, the rational, and the real. Okay? Now we've dealt with the -4, we can cross them off. Now we're going to deal with the next digit. The next one is a fraction, and it's a negative fraction. Where do we find fractions?
And just rational.
Just fractionals. Good. This is our fractions. And this is our decimals. What kind of decimals? Repeating and terminating. Good. So we have -3/4. It's going to fit in the rational, and if it fits in the rational, it always fits in the real. So we're going to down here, we're going to comma -3/4, comma -3/4. Okay? We've dealt with that number. Now we're going to deal with 0. Which box would 0 fit in first? The tiniest one first, Jay.
Whole numbers.
Yes, he fits in whole numbers. So then where does he go?
Then it goes like
Integer, rational, and real. Good. So we're going to have 0, 0. Okay, we're going to add 0 to the list with the other ones. So we've dealt with 0, we can cross him off too. Now we've got square root of 3. What kind of answer does that do? So remember, we always try to solve them first. It's irrational because it gives us what? A run-on. Good. It's a run-on decimal. So these guys are run-on decimals. So we found our first run-on, root 3. But if he's in here, the half is still part of real numbers. So he's always down here as well. So root 3. Okay. The next one, we've got 1/4. 1/4. What kind of number is 1/4? Can we solve it? Well, it gives us a decimal. Okay, it doesn't give us a whole number. What kind of number do we have? Yes, fractions are here. It's rational. If it's rational, it's
A real number.
real. Good. So we're going to have 1/4 in rational and 1/4 in the real. Okay? So we can take him off the list. Now we got the number 5. Where would the number 5 fit? What kind of number is he? Natural. So if he's natural, he's going to be whole, integer, rational, and real. He's in all of them but one of them. Yeah. He shares popularity to everybody, doesn't he? All right. So we dealt with our 5. Now we have what kind of a decimal? Well, what kind of a decimal?
Terminating.
A terminating decimal. So what kind of number? Rational and real. Good. So 7.3. 7.3. All right. What kind of a number do I have at the very end?
Irrational.
A run-on decimal. It's a run-on decimal, so that makes it the hat. It's irrational. So 1.2583 and so on. 1.2583 and so on. Okay? It's got to be part of this one and the box. So, it's kind of a trick question if you take a look, but the real number system should have had every number in our original list. because all of those numbers are real numbers. Okay? Good job, you guys. Okay, let's take a look what's next.
Where?
This concludes lesson 1.1 of Unit 1, Powers of Rings.